Hi, everyone.
Hi, Yann. Can you hear me?
I can, yes.
Awesome. Thanks for taking your time to be with us. R- to be with us. Can you hear me? Sorry.
Yeah, I can hear you fine.
Awesome. So I'm Alexander Antonio Juca. I will be the host for today, and I am part of the team at the APA conference. So it's basically the conference in Angola that deals with programming in Angola, and we basically our mission is to help programmers and software engineers in Angola and in Angola to be able to um, get to um, get to know the people around the world who are doing great engineering, great computer science, and connecting Angolan people to those people internationally. Can you hear me, Jan? Let me know as soon as you can hear me. Boa tarde, pessoal. Sou Alexandre Antônio Juca. Hoje, o objetivo é ter uma conversa, uma sessão de perguntas e respostas com o Yann Lecun. Vamos esperar um pouco para ele entrar novamente no stream. Estamos com alguns problemas técnicos. Yann, you back?
I'm back. It turns out my browser crashed.
Okay. Using Chrome, right?
I'm actually running Firefox on Linux, but
okay.
it was another problem.
All right. As I was saying, I was basically doing introduction, and basically APA conference is basically a organization that helps programmers in Angola to be connected with the developers internationally that are doing great job in computer science and software engineering. And the last time we had a conference, we invited a couple of people, including the creator of Python, the creator of C++, John Strostrup, and it was an excellent event. They were happy to be a part of this and to connect with people here in Angola.
Well, it's a pleasure to be here. I'm looking forward to your questions.
Awesome. So we're going to have a couple of questions, and then we're gonna leave a couple of seconds or minutes so that we can have questions from people who are watching. So one of the first questions we have for you, Yann Lecun, is since we are in Africa, can you tell us a little bit about what you know about deep learning in Africa? What are the things you are hearing about and the initiatives that are happening right now?
Okay, so I hear a number of things. I've heard from friends that there is an enormous amount of opportunities for applications of deep learning in Africa, and that motivates a lot of young people like you and others to learn more about deep learning because it could have a big impact on their country, on their neighborhood, their community, etc. And I agree with this. There is a lot of interesting things happening now. I think the future of AI and technology belongs to Africans because just from demographics, the demographics in Africa is such that this is where the young population is the most numerous, and this is where population grows, and this is where economic growth is the largest in the world. So there is like an enormous amount of opportunities for young people in Africa that, if they don't exist today, will exist in the near future. I mean, Angola is one of the countries that has the biggest economic expansion, right? It's starting from low, but it's progressing really fast. So I think there is that opens up a huge amount of opportunities, and really I think within a few decades, Africa will be a very strong force in technology in the world. I can't see that happening any other way because of demographics simply and economic expansion. So that's the good news. Of course, there are programs that have been started in Africa to sort of catalyze this. So things like the master's program in Ghana, run by AIIM, the African Institute of Mathematics, and I think those do a lot of good. There is, Google opened a lab in Ghana as well. The master's program is not in Ghana; it's in Rwanda, actually. But Google opened a lab in Ghana, which actually is headed by a former colleague of mine called Mustafa Cissé, who's from Senegal originally.
All right.
And also has he used to work at Facebook, so I kind of hired him at Facebook.
Oh, you know him.
I know him quite well. I also know quite well Yann Lecun, who is one of the members of that lab in Ghana, and he's actually from Canada and Haiti. His family is from Haiti, but he went to Africa to join that effort, and he also started his career. I've known him since he was a PhD student with Yoshua Benjo in Montreal, but he joined Facebook. He was one of the first people I hired at Facebook. But then, they had this desire to go back to Africa, and Google was in a position to open a lab in Africa. I should say that just in the last few days, Facebook has announced that it's opening an office in Lagos in Nigeria, and this is going to have engineering. So this opens up opportunities for young engineers in Africa who want to work in, AI, among other things.
Yeah, exactly.
And you see some of those popping up, in sort of various locations. So I think you see a lot of those things happening. There's, deep learning in Daba, which has been sort of a recurring event. Happening in mostly Southern Africa. Yeah. And so, it's happening. There are opportunities. It's usually the case that if you are in science, though, if you really want to push yourself, you want to be an engineer, you're curious, you want to know how things work so that you can, build new things. That's absolutely wonderful. And that has positive impact, regardless of what you do. You can also be interested in research, and for people like me, I always thought I would be interested in research, but I never knew I could actually be a professional scientist. Okay, until I got pretty late in my studies and I realized this is really what I want to do.
So what did it take for you to actually find out that that's what you wanted to do?
Well, so I went to engineering school in France. I'm French, right? So I grew up in France. I did all my studies in France, and I went to an engineering school. It wasn't a particularly top, brilliant, school. It was, kind of your average engineering school. I studied electrical engineering, and the more I studied, the more I discovered that I was interested in AI even when I was very young, but but I was interested in a lot of things that were kind of technical or scientific, and I was interested in computers, and I was interested in neuroscience and physics, and I realized that I was interested in doing research myself. I would read research papers and try to kind of understand where people came from and things like that. So I discovered that I was really into research, and that's what I wanted to do. I wanted to try to do, because you can't always succeed. And so eventually I found people who had similar interests, a lab that had similar interests in France, and I hooked up with them, and I went into a PhD program, finished my PhD, and then I moved to North America, not with the idea of staying. I had the idea of coming back to France after a couple of years.
Okay.
But here's the point I wanted to make with this. The point I wanted to make is you don't realize right away that you're good at something, okay? And you don't realize right away that what you want to do. But if you're driven, you should try. That's the first point. The second point is, if you really want to get into research, you should travel. You should go abroad. You should do an advanced degree either in your country or in another country, and then try to see what people do outside of your country. Get exposed to how people work outside of, because you're very sort of constrained by your own culture. This was the case for me. France has a long tradition in research and science, but I realized research and science in America and Germany and Canada is done differently. People have kind of different way of approaching it, and research and technology is really kind of a worldwide thing. So you should travel, get out, and then come back.
Okay. Those 2 points are very, very excellent points that you mentioned here. But regarding the second point, or from your perspective, from your experience, what was the thing that you found out was different in the way research was done in other countries that was really a turning point for you, that you said was really well done and that you could use in your own, that you could internalize and make it your own?
So it has to do with sort of with culture a little bit, and things have changed. I left. I finished my studies in the mid '80s or late '80s, so it's been a long time. But things have changed since then. But back then, in France, France is very likes mathematics. For a lot of French scientific culture, mathematics is at the top, right? And then you have things like physics and other things like that. And computer science is sort of is seen as a minor branch of mathematics in many ways. Okay, but I was coming to computer science from engineering. I was not a computer scientist. I was an electrical engineer, building hardware and things like that, and as well as doing software. And I found this sort of mathematical way of seeing things as very specific to France. You would go to America, and people would have ideas, and they would try those ideas and write them down, and not be shy about saying stupid things or asking stupid questions, and then try to explain things. So when you write a paper or something, in some European countries, you write a paper to impress your colleagues, right? So it has to be complicated.
Yeah.
In the US or in some culture, some subcultures in the US, you just explain your ideas. You try to make it actually easy to understand. And I discovered this when I joined Bell Labs, but also before that the papers that people read are the papers that are easy to read, not the papers that are sophisticated mathematically. They're the papers that are easy to read. At least in computer science and some parts of science. Mathematics is a different story. So explaining things well, which means understanding the core concepts about something, to be able to explain it in simple ways, is a very important skill that anybody can learn.
Okay, thank you so much for that explanation. So talking about mathematics and explaining things well, we know that in mathematics we have a fundamental theory of algebra, of calculus, and those sort of things. For our viewers watching, can you tell them if we have a fundamental theory of deep learning?
I wish there were, but there isn't. So there is there are a number of different fundamental theories of learning, machine learning in general, right? There is the, Vapnik's statistical learning theory. There is, various approaches from the Bayesian perspective. There is, people from physics, actually from statistical physics. The mathematics of machine learning and statistical physics is very similar in many ways. So some people who have contributed to this are actually come from physics. I think there's a lot of interesting things there actually at the moment. And those were developed, before deep learning really became prevalent. So they're more general. Some of them make assumptions that deep learning breaks, so they don't really apply to deep learning. But the challenge of developing a theory of learning and perhaps a theory of intelligence is not for older people like me. I just passed 60 years old, so
Yeah.
This is for young people like you to discover this. I'm too old for this. You need sort of new creative juices and new ideas, essentially, to kind of be able to understand this. There's a lot that we don't understand theoretically about deep learning system, and it's a fascinating area. I've been trying for many years to get mathematicians, applied mathematicians and physicists interested in deep learning. And it didn't happen until fairly recently, about 5-6 years ago. That's when those communities started really writing about deep learning and everything. So it's great, but I'm an observer of this, and a catalyzer maybe, but not a contributor.
All right, thanks for the explanation. So we know that we don't have a fundamental theory of deep learning right now. So what do you think? What are one of the problems that we are facing to get to that end? And what do you think the repercussions will be if we actually ever have a fundamental theory of deep learning?
Well, so the big question is, we don't even know what this theory would look like. What would it explain? So, for example, the normal theory of machine learning, statistical learning theory, like the Vaknip-Chervonenkis theory of learning, what it tells you is very general things. It says if you have a learning machine, that learning machine has to be specialized in some ways. It has to have a limited number of different functions that it can learn. Because if a learning machine can learn absolutely anything, it will require a very, very large number of examples, training examples, to learn anything. Okay? So the more general a learning machine is, the more examples it takes to train it, the longer it will take for it to learn anything. So generality is a trade-off, right? If a machine is more general, it might learn more things, but it will require way more data to learn it. So there are formulas that tell you, in the general case, if you have a learning machine, the error that the machine will produce on the test set will be equal to the error on the training set plus a gap called the generalization gap. And that gap depends on the complexity of the machine. The more complex the machine is, the bigger of a difference there will be between test error and training error. And then there is, regularization methods where you try to have something in your learning algorithm that, tries to kind of squeeze down the capacity of the learning machine so that gap gets smaller. And neural nets seem to be a little magical in that way. Neural nets break some of the formulas that statisticians have developed for decades that assume this. There's the problem of overfitting in machine learning. Yeah. If your neural net is too big or your machine is too big for the problem, it will fit the data, the training data, but it will not perform very well on the test data. Because of the problem I just mentioned. But if you use a neural net for some magical reason that people don't completely understand, the generalization is better than it should be according to the theory. We don't really understand this. There is some work on this. There seems to be some sort of implicit regularization in neural net that we don't understand. So that's that's something that's really worth understanding. There's some interesting work in this area at the moment.
And that's really interesting that we have these neural networks that are working. We don't need parameters for them, as they don't work as the statistical methods. We could just pass them data and they magically get to their conclusions. That's what getting to that step. What did it mean to you?
You mean what does it mean to me, or?
Yeah, what
I'm not
it
sure I
means to
understand.
you, the fact that we could now magically use these algorithms, these,
Right.
these these deep learning models that could do these things, but we
Yes.
don't truly understand.
Well, okay. So some of us have already, I've known for a very long time, since the 1980s, that neural nets work really well. And we've shown this on, a number of data sets and things like this. It wasn't enough to convince the entire community of machine learning that neural nets were a good thing. So there was a kind of a dark period during the mid-90s, between the mid-90s and the mid-2000s, where most people in machine learning thought neural nets didn't work. But a few of us really knew they worked. And because we'd run those experiments, we knew that even with relatively small amounts of data, which were big for the time but small by today's standards, neural nets could do a really good job. And we knew there was a big advantage in neural nets because neural nets can be fed with raw data, right? You can take an image, not pre-process it at all, or in very sort of simple, minimal ways, and then feed it to something like a convolutional net, and it will recognize images or speech or whatever, right? And you can't do this with traditional machine learning methods or pattern recognition method. You have to have a first stage that is handcrafted, that transforms the data in the appropriate way before you can stick a learning system, say a linear classifier, a super vector machine, or something like that can do a good job. So the sort of idea of end-to-end training was something I really believed in. I thought would inevitably come back to the fore, and it was the case also for Yoshua Bengio and Jeff Hinton and Yoga Schmiduber, a bunch of other people who are interested in neural nets. So that we knew this from the start. It wasn't a surprise to us, when people realized that we were trying to convince the community that this was the case. What was surprising is that it took so long, that it was so difficult to convince the community in computer vision, in speech recognition, in natural language processing, that those things actually worked, even though the data was there. But you have to understand something, which is in the history of science and technology, it's very often the case that people invent an artifact, a technological artifact, before theorists actually understand and explain why it works and understand how it works and its limitations. So going back to history, there is, let's take the example of optics. Okay, so people started building lenses, in the early Renaissance, and probably earlier than that, like actually the Middle Ages. But the understanding of optics, I mean, there were like studies by Arab scientists in the very early that tried to explain optics and the eye, etc. But really, optics wasn't figured out until basically Newton wrote down the laws of refraction, and that was hundreds of years after the invention of the lens and the telescope. The steam engine, okay? So the steam engine was invented in the late 1600s, early 1700s. It was, developed slowly. And then, physicists tried to kind of figure out what are the limitations of it. And that led to the Carnot cycle, the concept of entropy, and the proper definition of temperature and things like that, right? And it took over 100 years. Thermodynamics, which explained all those things, was not figured out until the 1800s. And so, and then thermodynamics became the foundation of a lot of modern science, modern physics, including modern physics. And so it's very often the fact that you invent something and then you figure out how to, what the theory behind it is. And we are in a bit in that situation with deep learning now, where we have an artifact that seems to work. It doesn't do everything we want it to do, but it does useful things. And we need to understand what the limits of it are, what the potential of it is, and how to make it better.
All right. Hopefully, what will happen is that we'll get a general theory before your time ends, right? In your time.
Yeah, I would hope so. There's something else I'm interested in. It's not just a theory. It's also like, how do we, get machines to be more intelligent than they are today, because they're not very intelligent.
Yeah, because people outside of the realm of machine learning and artificial intelligence and machine and deep learning in general, they have this this idea that AI might take away their jobs, and the fact is, whoever gets into machine learning or deep learning in itself knows that we are very far from that, right?
Yeah, so we're very far from building, intelligent machines with the level of intelligence that we observe in humans or even in animals. Like the most intelligent machines that we have don't have nearly as much common sense as a cat, any kind of animal you can think of, right? The type of learning that we observe in animals and humans is nothing like the type of learning that we can do with machines. So the type of learning that we use in machines is to train a machine is either supervised learning, right? You give an image to a machine, you wait for the answer, and you give it an image of a giraffe, right? And you wait for the answer, and the system says antelope, and so you tell it no, it's the giraffe, and then it corrects itself, right? So that next time around that you show the same image, the answer is closer to the one you want. So you give the machine the correct answer, right? And that's what like most of machine learning is based on this. Then there is reinforcement learning. You don't tell the machine what the answer is, you just tell it whether the answer it produced was good or bad. And then there is something not very well defined that I call self-supervised learning, that some people call unsupervised learning. And it's more of the type of learning that we observe in humans and animals. This is learning to understand the world by observation and learning a lot about how the world works, right? So baby humans and baby animals learn very quickly that when you have an object and you hide it behind another one, the object is still there, right? That's called object permanence.
Yeah.
That's learned pretty early on. Babies learn, not so quickly that objects that are not supported fall, right? The fact that gravity has an effect on objects. Babies learn this by the age of 9 months, roughly. It takes about 9 months for human babies to learn
that
the effect of gravity. Okay, to be surprised by the fact that an object floats in the air, for example. That's how we know what babies learn. So, babies are not taught supervised that objects fall. They just observe, right? They observe the world. They barely interact with it actually in the first few months, and they learn an enormous amount of background knowledge about how the world works just by observation. We don't know how to reproduce this kind of learning with machines, and in my opinion, I don't think we're going to be able to build truly intelligent machines until we find ways for machines to learn this way by watching YouTube videos or something, right? So that's called a part of that subfield is called self-supervised learning. I've been a big proponent of it. If you're interested in this, you can watch some of my lectures on this. I'm mostly sort of trying to get people interested in the problem and maybe framing the problem in a particular way, but I don't actually have solutions to it. Okay, this is a research program. Now, there are forms of self-supervised learning that have been applied to natural language processing and to computer vision that are incredibly efficient. They work really well. So all natural language processing systems today are based on a phase of learning, which is essentially self-supervised learning. So some of you may have heard of models called BERT, right? This was a paper by Google a couple of years ago, and there's been like a lot of follow-up work, including from Facebook, Roberta, and XLM, a bunch of things like this. And the idea of you pre-train those things. Those are big neural nets, and they train on text. And the way you pre-train them in self-supervised way is that you show them a piece of text, typically a few hundred words, and you take out 10 or 15% of those words. You mask them. You replace them by an empty marker if you want. And then you train this enormous neural nets to predict the words that are missing. And in the process of doing so, the system learns the structure of language in to an extent that is really surprising. So then you can use the representation extracted by such a network of a text as input to a subsequent system that will do, translation, text understanding, text retrieval, whatever task you want it to do. That's been ridiculously successful over the last year or two, and it's revolutionized natural language processing. Translation system, it enables, for example, the possibility, which is something that's very relevant for Africa, it enables the possibility of translation from any language to any language, even with a limited amount of data, of training data between the two languages. And so that could be very useful because there's so many languages in Africa.
Yeah.
I mean, everyone speaks two or three languages or four languages, right? I mean, you speak Portuguese and English and probably a bunch of others, no?
Yeah, I speak 5 languages right now.
Right, here you go. I only speak 2 and one badly. So
Yeah, I think that would be a very interesting thing to apply in Africa. We have in Africa we have a huge set of problems that could be solved using technology. So let's go to topic. Let's talk about the papers that you've read in the last couple of years. Let's say the last couple of 4 years. What are the papers, scientific papers in deep learning and artificial intelligence that really that you thought was really well done? That you looked at the paper, you read the paper, you looked at the fundamental idea, and you said this was something really interesting.
Right. So there's a number of different things that are interesting at different levels, right? There are papers that take existing methods, they tweak them a little bit, they scale them up, they apply them in very smart ways to a big data set, and they get a result nobody had obtained before. Okay, they get better results on translation, let's say. So to take this is going to sound a little parochial because I'm going to talk about some work that comes out of Facebook AI research, but this really interesting work on translation using very, very little supervision. So here's a very interesting fact. If you use one of those techniques I was describing to find representations of text using self-supervised learning by basically predicting missing words in a text, you now have a system that can extract representations of words or expressions or longer text. And those representations are in the form of a vector, okay, a list of numbers that basically describe the content of the text in terms of what does it mean? Is it a verb? Is it, does it describe a situation or an action or other people involved? So, those representations like encode everything there is to encode about the text that would be useful for the prediction task. Now, if you do this, if you train a system like this on, let's say Portuguese, okay, it will it will associate a vector to every word or expression in Portuguese. And then you do this for, some other language that's completely unrelated. Okay, let's say Urdu, okay, which is spoken in Central Asia, right? There's probably a fairly small amount of training data that we can use to train a translation system to translate from Portuguese to Urdu. But we can train the system to represent Urdu the same way as we did for Portuguese, like completely independently. Okay, train one of the systems to predict missing words in Urdu text, and then this system will extract a representation in form of a vector of every word in Urdu or every expression. Now it turns out, so essentially a language is now represented by a cloud of points, a cloud of vectors in a high-dimensional space. Now you have the cloud of point for Portuguese and the cloud of point for Urdu. It turns out those cloud of points have similar shapes. So now what you have to do is kind of find a way to kind of match them with each other so their shapes, the global shape match. And what you have now is a translation system. It's not a perfect one, but it's a pretty good one. And so here is an example where you can create a translation system through self-supervised learning without having any parallel text between the two languages. People are now trying to do this. So there are techniques now that have been improved that use a little bit of parallel text, but they basically represent text independently of language, right? So those are things like they call XLM, right? Cross-language language model. So you train a system like this. You don't have independent systems for every language. You have a single network that can handle all languages, and it can accept a text in one language and decode it into the same language or another language. And what you get in the middle is some representation of text that's independent of language. You can use this as the basis of a translation system. Facebook uses this on a very large scale because Facebook has to do content filtering and content moderation in every language. For example, to stop hate speech, things like that, right? And it has to work in just about every language people use on Facebook, which is a very large number. We don't have training data for all of it, so we have to use a system like this. I mean, this is fascinating in my opinion. So I mean, a lot of things in this area of self-supervised learning for text and BERT-like systems, I think has been really interesting and revolutionary. What I'm interested in, as I was telling you before, now is approaches to self-supervised learning. So basically, techniques that allow you to do prediction, not just text, which is the case for the systems I just described, but for things like video. Like we train a system to take video frames and then predict what's going to happen in the video in the future by just observing, right? You just feed a video clip to a system, show it the beginning of it, and ask it to predict what's going to happen next.
Mm-hmm.
And the problem there is very complicated because there's many things that could happen in the future that are all plausible, and you're only going to observe one, but you have to have a way for the system to represent all the possible things that could happen. The instinct for most people in machine learning is to say, well, you don't want to represent a single outcome, you want to represent a probability distribution over outcomes. But we have no idea how to represent probability distributions over video clips. We don't know how to do that. And so that might require new math, new formalisms, right? New ways of thinking about this.
Okay, so that means there's a sort of we need to get into field of mathematics to be able to reach that level of problem solving, right?
Yeah, how to represent uncertainty, how to represent multiple outcomes. I mean, basically, what it comes down to is think of a neural net that instead of producing a single output, it produces a whole range of possible outputs, possibly a continuous representation. But if you immediately go to representing probability distributions, you run into mathematical intractable problems. And so we might have to, think about new ways of representing uncertainty that is not probabilities, essentially.
Because while you were explaining it, I was thinking of how more computationally, how much more computational power we would probably need to use to be able to solve such a problem.
Yeah, I don't think it's. I mean, more computation is always better, but I don't think it's the crucial issue there. I think it's more like new concepts, new ways to think about the problem. Let me give you a very concrete example. And again, there's talks about this that you can watch that I've given on this topic in various places. You can find them on YouTube. If I do the experiment, right, I put a pen and I let it go. The pen will fall, right? And every time I repeat the experiment exactly identical, it will probably fall in a different direction. Okay, so here's an example where if I train a neural net where the initial segment of the video is me putting the pen exactly at the same place, always the same way. And then every time the rest of the video is different. How can the network predict? The network has to figure out that, the pen is going to fall without predicting in which direction it's going to fall because it can't predict that. So it has to form a representation of the fact that the pen is fallen independently of the direction in which it's fallen. And it's a problem of learning a representation of all those outcomes. Okay, it's not, you could try to figure this out by some probability distribution over angle. It's easy in this case, but think about a general video where an infinite number of possible things could happen in the future. How do you represent that? So that's a big puzzle. It's the biggest puzzle in AI for me. Like this is the thing I'd like to help to solve. I'm not sure I'm going to be able to solve it before my brain turns into white sauce. Okay.
It's quite an interesting problem because from what we have in probability and statistics, like you said, we don't have the mathematics right now to solve it. We don't have it right now. So let's connect this idea from mathematics, how mathematics helps computer science and artificial intelligence, and how physics does the same. We see how mathematics help get we find new ways of solving problems, and then with ideas of physics we found new theorems, or we find new ideas that we could apply in mathematics. Can we find new ideas from physics that would help us find these help us improve in artificial intelligence in a way?
Yeah, and it's quite possible that the mathematics that will come out of it that will be useful. I mean, it's already the case in certain areas of machine learning, that this mathematics is going to be very similar to the type of mathematics that physicists used in thermodynamics or statistical physics. So things like there's a set of techniques that's very fashionable right now in machine learning called variational methods. So variational methods are, they apply generally to learning systems that have an input and an output, but internally they have a latent variable, which is a variable that you need to compute the output of the system, but its value is not determined by an input or anything. It's a free variable that you can choose its value, or you can sample it from a distribution. If you have a system like this, training a system like this that has a latent variable can be very challenging, and so people have developed those techniques called variational methods, and the mathematics of it comes directly out of thermodynamics. It's the same mathematics. So there's notions of the energy is like the objective function you're minimizing. The energy in physics is like the objective function you're minimizing. Then there is a notion of temperature. There's a notion of entropy, which is basically how much information are you missing about the value of the latent variable. And then there is a notion of free energy, which is the quantity you can actually minimize. But it's intractable, so you have to find mathematical bounds for it, and you're going to minimize a bound on the value you actually want to minimize. So those are variational methods. I mean, what I'm saying here may not make any sense to you, but it's not that complicated in the end. And there is a lot of recent methods like variational autoencoders that have come out of this way of thinking about things. The idea of using those techniques in the context of machine learning dates back to people working on Bayesian nets and graphical models and things like this, where those variational methods came about. Jeff Hinton had been proposing things like this since the early 1990s, actually, in the context of machine learning. So there is, that's where the connection is made, and which is why I expect, a lot of things there to happen in this context. So there's two things about mathematics, though. One thing is that mathematics can help you conceptualize something, and can analyze why a system works and what the limits of it are. But sometimes it can also limit your thinking. It has caused, in the last couple of decades, the machine learning community, for example, was rejecting neural nets and was hung up on particular types of machine learning algorithms just because they were easy to understand mathematically. And just because you could do cute math about it, okay? And heuristically it's wrong, because you're limiting your thinking because of the type of mathematics you can do. It's the wrong way to think about it. You have to think about artifacts that work, and then use mathematics to kind of explain why they work, which is the way history has worked in the past. I actually gave a talk on this at the Institute of Advanced Studies in Princeton a couple of years ago, or a year ago or so, and it's called On the Epistemology of Deep Learning. You can watch it; it's on YouTube. So, if you're interested,
thank you for that explanation. I'll definitely I'll take some time to watch that. So, Yann, we have a couple of questions from our viewers, and one of the first questions we have here is from Elio Fernandez. I'll show the question up here. He says, "Hello, Mr. Yann Lecun. I would like to know specifically what is the reporting structure for an AI team?"
Okay, well, there's different types of AI teams. There is research teams, applied research or advanced development teams, and engineering teams and product teams. And they are organized very differently, right? Let me start with research because that's what I know best. So a research organization, a fundamental research organization, has generally a fairly shallow management structure, and maybe 2 or 3 levels or something, and is bottom up, which means that the researchers, the scientists decide by themselves what project they choose to work on, because it's exploratory research. So if you try to sort of organize people too much, you tend to kill their creativity. So you want it to be bottom up, okay? And you want all the management chains to be scientists, all the way to, the top management of the research lab. Then you have applied research, advanced development. And so what I should say also about fundamental research is that a lot of the work is done in collaboration with universities, with visitors, with everything is published, almost everything is open source, etc. Right? So it's really research. Then you have advanced development, and generally those projects, a lot of them get published as well, but most of them are more directed towards some internal goal. So, you want to improve translation, you want to improve, image understanding, for content filtering, things like that, right? You don't develop products, but you develop technology that will be used in products. And, those are more organized in teams around projects, whereas research is more by discipline rather than by project teams. So there it's organized by teams, and then there is product groups that basically use that technology, and they use them in products, and those are much more focused with shorter deadlines and things like that. So it's very different. There's a whole spectrum of different things.
And I think they could vary depending on the company, right?
Yeah, right. So I mean, most companies don't actually have fundamental research labs, or very, very small ones, or small ones that don't last very long. So the ones that have fundamental research labs can be counted on the fingers of one hand in the world.
Okay.
I mean, that includes Facebook, Google, which includes DeepMind, and there are kind of pockets of really interesting research at Intel and NVIDIA, and there's certainly IBM. Microsoft Research has a long tradition of that as well. So that's about 5. I mean, there is a bunch of others, of course, who would be very upset at me if they heard me say that. But
so Yann, we have a couple of other questions here. We have a questions from Armstrong. His question is a question for Yann Lecun. From a pioneer point of view, as an emerging technology, modern AI is developing very fast, making it difficult for pioneers in the field to catch up. What do you recommend for people interested in learning artificial intelligence? And thank you for using your precious time to talk to us.
Yeah. I'm not wasting my time here at all. I know I'm not. So it's very hard for me to follow actually what goes on in the field. I can't follow everything anymore, because the field has grown so much. It's so diverse that I have a very broad view of what people are doing generally, and I can fit this to my mental model of where things should go. But there is a lot of details that many of you here listening to me probably have much more knowledge about than I have, including on topics that I've worked on, many years ago. Mm-hmm. Ask me what are the big trends that I think are going to be important in the future in machine learning, and I'll tell you right away, it's self-supervised learning. This whole idea of pre-training a system using unlabeled data, that's going to be big. If you want to work on some interesting problems at the forefront of research in AI, that's probably where you should be working. It's not the only thing, okay, but that's a good area to work on.
So would you suggest that anyone who comes into the field right now focus on a very specific field for a while instead of focusing on many fields at the same time?
Well, you have to it's a combination. So you have to build your own idea of what you think is important from very basic principles that a lot of people in the field, you look at all the papers that are published at the conference, and many of them seem very, very narrow and specific, right? And you have a hard time understanding why people are working on those. There's many reasons why they work on a particular topic. One reason is because it's going to get them a paper at the next conference, but which is not a good reason. But generally, what happens is that you start with a very big, grandiose, ambitious idea. I want to make machines more intelligent, and then you realize how can I do this? What problems can I attack that will make progress? And the more you progress, the more you read about what other people have done, the more you kind of narrow your interest to kind of a small problem. You realize, actually, I think AI is limited by how fast we can train things. So we should develop new parallel architectures, computer architectures that can, parallelize a lot. And then you realize, oh, but we don't actually have good optimization algorithms like stochastic gradient that parallelize very well. So maybe that's what I should work on, parallelization of stochastic gradient algorithms. And then you realize, oh, actually, the main problem is that we don't have the right architectures, to train systems to understand text or to do reasoning. Like, current AI systems, deep learning systems, don't do reasoning very well. How can I develop a system that can not just, recognize images or speech, but can reason, can plan ahead? Okay, so maybe I should get interested in robotics because that's why people are interested in planning. Maybe I should read, papers by Chelsea Finn and Sergey Levin and Peter Adil, because they are the ones who are kind of working in this area, or Laurel Pinto, or Abhinav Gupta. I mean, those people who are kind of interested in, learning models of the world for the purpose of robotics. And then you realize, oh, okay, there is a supervised learning environment, but, robots and people learn interactively in a environment that changes all the time. What the example they see depends on the action they take. So perhaps, I should think about like creating virtual environments where machine learning systems can interact with the world instead of just being fed examples. There's a number of projects like this at Facebook and Google and various other places. That's the kind of stuff that people working on autonomous driving are working on. Okay, so there's all those things, and then more general problems like self-supervised learning. This is what limits us. You have to sort of identify what you think is a limitation, and then work on this. This is at the kind of general method level. And then there is applications, right? You say, oh, there's this problem that I'm familiar with because I grew up in this area where, they don't know how to predict crops and, whatever. And perhaps there is some way of doing this, or, using machine learning for, crop management that people hadn't realized before, or transportation systems, or autonomous drones that can kind of drop things in isolated villages or whatever. So that's application driven, or systems that can monitor wildlife, or etc., or solve social issues, social problems, or improve education. There's going to be a lot of use of AI system in education, or very simple things, very basic things like. Okay, I'm in a country where there's very little services that people can have access to, like healthcare or banking or things like this. Like how can technology help that? It's not just access to the internet from your mobile phone. It could be I need to buy something or talk to a remote doctor, and I need to identify myself. So I'm actually co-founder of a company that works on, basically biometric authentication, and most applications are actually in the developed countries that don't have infrastructure for this otherwise. So yeah, I mean, you can approach this from lots and lots of different viewpoints.
All right. So basically, from what I understood from your answer is that you can start from a broad idea, like a big question, and broaden that idea into a specific narrow field, and then focus on those specific questions and try to answer those questions. So
that's right. But
right.
Always understand the context in which you're doing this, right? So Richard Feynman, who's Nobel Prize winning physicist, very famous physicist, said the best way to kill your creativity is to read everything about a topic before thinking about it yourself. So if there is a problem like this, you can read about it in general terms, more kind of grand visions or philosophical terms, and you form your own internal idea about the problem. And then you read papers, and you realize what people have done, and you realize probably a bunch of people have thought about this the same way you did. Or maybe you realize that you have an original way of thinking about this because your background is different, because the thing you went through in your education is different, the way you approach things is different. And so that means you might bring something to the table here because you think differently from people who came before. that's how innovation and invention comes about.
It's about,
You
yeah.
you think about a problem differently from everyone else.
So we have 4 minutes with you, 4 more minutes. So a couple of seconds ago, you were talking about how basically reinforcement learning. And can you tell us about how reinforcement learning is being used in games right now? Because what happens is, I know a couple of people in Angola who are really interested in building games, and we have the question of how do we build smart enemies or players in the game?
Right.
Uh, how so, can you tell them how these systems are built, and how this is probably connected to reinforcement learning?
Yeah, I'm a little immersed in the gaming culture because my sons are game developers, but I have three sons and they are into game design. But the yeah, so you have to realize something, which is reinforcement learning. The most impressive applications of reinforcement learning have been in games, and you have to ask yourself why. Okay, so games are generally activities that are designed to be difficult for humans, which is what makes them interesting and challenging, right?
Right.
So humans, when you look at chess or Go, which are strategically, basically based on strategic planning, humans are actually very, very bad at this. Humans totally suck at chess and Go. All right.
Yeah.
And we realize this because computers are so much better than humans at it. Okay. So AlphaGo and its successors. There is an open source Go implementation from Facebook called Dark Forest, or Elf Open Go. Actually, it's called. You can just download and play with the code, and it's has superhuman performance. It can play millions of games in a few hours on a large GPU cluster, and basically reach superhuman level by training itself using reinforcement learning. So what it tells you is that humans are just very bad at this. Okay,
Right.
machines are much better at planning. Now there are games that until recently resisted kind of computer implementations, and that includes games like poker, where a lot of it is kind of knowing what your opponent will be. So there's been recent work. Actually, the main person working on this is at Facebook now on poker players, and they've been working on another strategy game now called Diplomacy. So Diplomacy is really complicated because it's kind of a strategic game where you have to form alliances and things like that, and they have a system that works pretty well for this. So there's a lot of things for games, but why does it only work for games? Why is it that reinforcement learning works for games and is, despite many attempts, doesn't work very well for like autonomous driving or robotics? And the reason is it requires too many samples to train. So,
Okay.
In a game like chess, you can, play millions of games on the computer and, they can go pretty fast. But if you want to simulate a car driving and, accurately, it's very difficult. So reinforcement learning has had very few applications in the real world, except in situations where you can have, essentially millions of samples without paying for it. So, for example, you are Google and you want to figure out, should I put this search result here or there? Which one should I put first? You can just look at, how many people click on each of those and then sort of adapt your prediction system. It's not really reinforcement learning. It's more like, learning to rank, but it has some similar flavor. There's a lot of applications of that for, ranking, ad placement, content ranking, and various control systems. DeepMind has built a couple for Google.
Yeah. Thank you. Thank you. Thank you so much for we reached the end of our discussion right now. Looks like it's 3 o'clock here. And it was really interesting having a conversation with you, and seeing how people in Africa are actually working at Facebook and doing great things at Facebook, and how they're coming back to Africa and giving back to the community. And we can see the initiatives that Facebook has taken to build these kind of labs in Africa is really going to be a very a huge supporting backbone for all of us in Africa. And hopefully that will attract more young people in Africa into the field.
I mean, yes, you have to give young people opportunities, in their country or their continent, to kind of motivate them to work in a particular area. And I mean, people like you from what we talked about yesterday in preparation for this, I saw in you, myself when I was young, because we have a drive to basically understand, technological artifacts and science, and so we can't help it, right? I mean, despite regardless of what environment we're in, this is something we have to do because that's what drives us, right?
Exactly.
But then you have to give people opportunities to kind of use their their skills, and improve the condition of their own countries. That's true everywhere. And sometimes that means leaving your country for a few years and coming back. Not always, but sometimes. It was very useful to me, and to a lot of people I know. And so, as I said, you guys are the future of science and technology. You're the Africa is the future of this, just because of demographics.
Yeah, thank you so much. Hopefully, in the next 5 to 10 years, you see a really good scientific paper from Angola. This is encouragement for all those people watching us right now from Angola, and hopefully we get students who are studying right now who work hard in computer science and engineering, and really build these kind of systems that not only solve problems locally, but in the world. And would like to thank you once again for taking your time and speaking with us from Angola. And I believe a lot of people who are watching right now are looking at you and saying, okay, I see myself in this man, and I see myself working in this area of science. And I think you being with us, you inspired a whole generation of people to get into the field, and I much appreciate that.
Well, I'm really looking forward to what you'll be able to achieve over the next few years and decades. I think it's going to be really awesome to watch, and I'll help if I can. So it was a real pleasure to speak with you.
Thank you so much. Thank you so much for your help.
All right.
All
Bye-bye,
right.
everyone. Take care.
Bye bye. Bye bye.
And good luck with your work. And
Thank
your
you.
studies.
Thank you.